All right, so the first problem, which is supposed to be problem number 1, but it looks like it got cut off. They give us this equation, or this function. All right, so the first thing they want you to do is they want you to find the derivative. Pretty easy to do, 4x minus 1. Agree? All right, and then I realized after I helped a couple of you, I didn't tell you what instantaneous rate of change is. That means basically what you're going to do is you're going to take -1 and you're going to plug it into the derivative. Okay, so this is going to be 4 times -1 minus 1, which is -4 minus 1, which is -5. So this yields me this point. This is from the derivative. Letter C gets goofy, though, because it's asking you to say, hey, what's happening at -1 of my original function? So you take -1 and plug it into your original function. -1, there's 2 negatives there. So that's going to give me just 2, and that's going to give me +1, so that's going to give me 3, which yields me this point here. So this is on actual graph, if you were to graph it, and this is on the derivative. And yes, you can graph the derivative as well. In fact, let's take a look at what the derivative graph versus the original graph looks like. And Desmos does it really nicely. So, and it kind of gives us a brief understanding of what a derivative does to an actual graph. So if I have y equals, my original was 2x squared minus x. And then let's do another graph. We'll do this one in blue. And so the derivative is y equals 4x minus 1. So notice, you go from a second degree polynomial to a first linear polynomial. Okay, so those are some things that take place. And then when we had taken that -1 and I plugged it in, let's see. So let's do this. We're going to do -1, -5. Go down here. -1, -5. And then the other one was at -1, 3. Is that what it was?
Yeah.
All right. So notice what we had found. The very first point, -1, -5, was a point that was on the derivative, whereas -1, 3 was a point that was on the original function. So it's just getting to my perspective of sometimes what happens with a graph, the exact same point actually won't be the exact same location from a regular graph to the derivative graph or vice versa. Okay? Everyone's on this 4-3? Everyone's good? Even Mechanic is ignoring me. It's like having my wife here. I'm telling you, I just can't take him anywhere. All right. Problem number 2, we then come across a graph that looks like this. They have this as point A, point B, point C, point D, and point E. And then we have from like this point to here is little a, and then little b does here to here, and then C is basically going from here to here is little c. Those are just intervals, and then little d goes from here to here. All right, so we have to be aware of what things are going. So for letter A, this is problem number 2. Letter A, over what intervals A through D is the rate of change positive? Whereas f at x positive. Okay, so this would mean where would the slope increase? Okay, so as you go right, it goes up. Okay, so over what intervals from little a to little d is it increasing? Well, it's increasing from B, so this is all increasing. It's also increasing on A, but if I use B, B includes that whole thing. And then it's also increasing at D. So this region here is where our graph is increasing, and then also here our graph would be increasing is what we're looking at, okay? So what that's going to start leading us to is we'll eventually get into something called a sine line, which a sine line from a derivative will kind of give you an indication of what the original graph would look like. You won't know the exact value, but you can give a pretty good guess. And then letter B says, over what interval is this negative? Okay, so that would be slope decreasing. Okay, so that looks like just this region here is where it's decreasing. So that would happen at little c. Excuse me, I'm blowing out. All right. And then letter C says, where is f at x equal to 0? Okay, so this is going to happen at point A, point C, and point E. So this happens at point A, C, and E. Okay, and the reason that takes place is that's where it goes from being, decreasing to increasing or increasing to decreasing. There's a sign change that takes place, and that's also something I will tell you once we start looking at it a little bit further into derivatives, where you have critical values. Critical values is where things are changing direction, things like that. All right, number 3. Number 3. Let me squeeze that in here. Yeah, I'll extend the page. Do it in hot pink. So number 3 says at what points A through E does it change from, we want to know where it goes from positive to negative. Okay, so we need to know that this is a positive slope, this is a negative slope, this is a positive slope. So we want to know where does it go from being positive to negative, and exactly at point A is where it goes from positive to negative. Okay, if you chose point C, it's going from negative to positive. You can't really choose point E because we're just talking about basically the interval. Okay, we might be able to get away with saying, because we can see the graph, we could say that this is also decreasing here. So point E, I guess you could technically say would also work as well, because it went from a positive slope to a negative slope. And because I could see more of the graph, we could make that conclusion. And then for letter B, pick another vibrant color. How about orange? So that's the answer for A. For B, where does it go from negative to positive? And negative to positive has to be at point C, which is right here. Okay, because I went from a negative slope to a 0 slope to a positive slope. Questions about my artistic ability or math that we have? All right, then we go to number 4. And it says find the derivative of each. So y equals 4. So what's the derivative of a number?
0.
0. Cool. And then number 5, they give us g at x. We have this whole equation, 10x to the 9th minus 5x to the 5th plus 7x to the 3rd plus 5x minus 6. If I wanted to find the derivative of that, I'd say 90x to the 8th minus 25x to the 4th plus 21x to the 2nd plus 5. You don't have to worry about taking the derivative of negative 6 because that would just be 0. And there's your answer. And then number 6, they're trying to sneak in, but mine's covered. I can't see a 6, but it'll work. So we have x to the negative 5 plus x to the negative 8 minus 3x plus 10. So if I want to take the derivative, okay, so I'm going to get negative 5x. If I subtract 1 from negative 5 minus 1 is negative 6. And then I'm going to get negative 8x, subtract 1 from that, so that goes to the negative 9th. And that's to the first, so the derivative of that's just going to be negative 3. If you clean this up a little bit, negative exponents will drop back down to the opposite location that they're at. So if they're a numerator, they drop to denominator. If it's a denominator, flip it back up. So this is the cleaned up version. Okay. The above is not technically wrong, but if the teacher asks you to clean it up, you'd get through there. So if you got down, if this was a written problem, if you gave me the very top, the negative 5x to the negative 6, that answer, I'm going to count it correct. Okay? All right, so let's pause there because number 7 gets a little bit goofier. Any questions on any of those? Excuse me. Good. Can I move off this page? Number 7, we have f at x equals 3 over x to the 4th plus 2 over x to the 5th plus 5 third root of x. All right, this one, you have to rewrite it to where you don't have denominators with a variable. So I get 3x to the negative 4 plus 2x to the negative 5. And then you have to realize there's a 1 here. So that's plus 5 raised to the 1/3 power. Okay. Oh, I forgot the x. 5x. X is raised to the 1/3 power. All right. So if I want to take the derivative of this, I'm going to get negative 12x. Make sure you subtract 1 from that to the negative 5 plus, minus 10x. Subtract 1 from that, so I get negative 6. And then I'm going to get 5/3 x, and I have to subtract 1, which is the same thing as negative 3 over 3. Okay, I'll put a little one. Same as negative 1, which gives me negative 2/3. And then we can clean this one up a little bit to say, well, that's going to be negative 12 over x to the 5th minus 10 over x to the 6th plus 5 over 3 x to the 2/3 power. And I'd say if you can get to that point, you did very well. If you can get to the blue, that's awesome. If you can get to the black, even better. That just shows that you have an understanding of a negative exponent swaps locations. Okay. All good? All right. I'm going to show you something that will go along with 8, 9, 10, and 11, but I don't have notes for it. So I'm just going to show it, and I'll leave it up there. I only really have to do one problem because they're all basically done the same way. So this is an example that you don't have. Let's say we had an equation that looked like this. Okay, and we want to know two things. The slope of tangent line at -2. Let's go with that. And then the other one I want to do is we want the equation of tangent line at -2 as well. Okay, so first thing we want to do is this. We want to figure out the equation of the tangent at -2. So I'm going to get -2 comma something. So I'm going to plug -2 into the original. So that's going to give me 3 times -2 squared plus 5 times -2 minus 1. So that's going to give me 12 minus 10 minus 1. So that's going to give me just 1. So this means the point -2 comma 1 is a point on our original graph. We're going to save that for a moment. Okay, does that make sense? We're going to save that -2 comma 1 for a moment. Next thing I want to do is I want to take the derivative of our function. So that's going to give me 6x plus 5. And to find the slope of this, I'm going to take that -2 and I'm going to plug it in, which is -12 plus 5, which is going to give me -7. So this is the slope of our tangent line. Okay? We're almost done, but I want to show you what we're doing on Desmos before I go further. Can I move on? I'll come back to that page. All right, so let's clear these things out. So I get y equals 3x squared plus 5x plus 1. Plus 5x minus 1. Okay, so this is this particular graph. Okay, now I could graph the derivative. So if I graph the derivative, let's change that color. So y equals 6x plus 5. So the green is our derivative. So something I want to show you about the derivative that you might not know. So we went from a quadratic, the first derivative of a quadratic is linear. So quadratic means parabola, linear means it makes a straight line. Okay. Do you see this point right here that crosses the x-axis? Actually, if I highlight that point right there. So at -0.833333, that value is the same value x-wise as this value down here, the minimum. Okay, so that basically means that our derivative, let's see if I can come down here, give me that. So right there is my vertex of this parabola. So notice where the derivative is crossing the x-axis, that showed what we're going to call a minimum value. Yeah, we're going to change that to local min or local max, but where our derivative crosses the x-axis means that on our original function, our blue function in this case, the equation exactly at that point is going to be it's going to be a horizontal sloped line. Okay, in this case, it's going to be y equals 3.083333. Okay, so that's an important value to know. So y equals negative, I forgot what it was. Negative 3.08. Oh, shoot. Okay, so that purple line is where the direction of our parabola changed from going down to going up. Okay, so that's kind of just some visuals of what's taking place. So now I'm going to get rid of these two portions and keep my parabola there. And we want to know what the equation of the line tangent at -2 would be. Okay, so I think I had the point -2 comma 1, and I also had m equals -7. So if we call this x1 and y1, we have to go back to algebra 1 and remember our point slope equation. So if I go plug values in, I'm going to get y minus 1 equals -7 x plus 2. And if I graph y minus 1 equals negative, and I don't have to go clean it up. I don't have to put it in slope-intercept form. If you use Desmos, so it'll take it just like that. So I'm going to graph y minus 1 equals, and we said -7 and then x plus 2. Okay. All right. So we said the point of tangency was the point -2, -1, or +1, excuse me. Okay. So this point right here, that point right there is where our line tangent, meaning our tangent line, will touch our original function. It touches our original function at that one location right there. So at the point of tangency is at point -2 comma 1. So that's why I kind of plotted this point. So I have my original function here, and this is the point, the equation that is our point of tangency. So if you're given a value, you have to find out what value would have existed on the parabola. So that's why we would have taken the -2 and plugged it back into our original. And then we have to use what that value was, and you have to find the slope. So you take the derivative, plug that in, and find you the slope of our equation, or linear equation in this case. So most of the things that we'll deal with in here, I'm not saying they don't exist, we will usually always keep them as polynomials. So I normally won't get anything real crazy. I mean, if you take another calculus classes or pre-calc classes, there's some crazy equations you've dealt with. And we've seen some crazy ones in here. But as far as the derivatives go, so basically, that is your information that I would have given you notes on. So on that backside, will you try problems 8 through 11 that are all done the same way? I will tell you that number 11 might be a little trickier because you have root x, change root x to x to the 1/2 power. Deal? All right.